So we've been talking about the laboratory measurement for electromagnetic waves, especially the low frequency measurement in the last two classes. And today we'll talk about the high frequency measurement and how to extract the permittivity or complex permittivity value from the equivalent circuit analogy. Okay. So in the high frequency measurement, unlike the low frequency measurement, you have wave propagation phenomena because the wavelength is very low and very short, but the skin depth is very short. So when you emit the wave to the medium, like the soil medium, the penetration depth is in the order of several millimeters. So you have only the local measurement, but you have coaxial cable which guides the wave, and there's an end of the coaxial probe, and at the end of the probe there's a wave emitted from that probe. So here you can see that this is the wave guide and this is the coaxial cable. So if you connect this probe to the electronics like this will be the high frequency impedance analyzer. Then this emits could be a sinusoidal wave, and then it detects the reflective wave from the specimen. Okay. And the penetration depth of the wave generated is only in the order of few millimeters, so it can reflect the property in that local area. This is a very expensive equipment actually. Could be tens of $1,000s maybe. So in the proof is designed with the wave guide. So there's a transmission line, and this probe detects the reflective wave. So let's say that this is the specimen, the gray area. Then when there's an incident wave generated from the probe, then there's a reflection because of the impedance mismatch. So this will be the free space. And this is the specimen. And because of the impedance difference, this is the specimen, and this is the impedance of the free space. Then you have a reflective wave, and by comparing the magnitude and the phase shift between the incident wave and the reflective wave, you can calculate the complex impedance. Okay. So that's the same principle that we have learned for the low frequency measurement. And the other case is you can also, on the top of the reflective wave, you can also measure the transmitted wave. And then you have one more information so that you can solve with the more accuracy. And we'll see how it can be applied. So let's think about the reflection method. So in the reflection technique, the complex reflection coefficient R star is determined by comparing the reflected signal E and the emitted incident signal EI. And the complex value reflection coefficient captures both the phase and amplitude information. So this is the definition of the reflection coefficient, right? So when you recall the materials that we learned for reflected wave and refraction and the transmission coefficient, right? And this is the reflection coefficient, and the materials impedance and the free space impedance. And you can manipulate the equation to get the materials impedance, right? G star, right? From the reflection coefficient. And according to the wave propagation equation, which is a function of the magnetic permeability and the permittivity, of material and the frequency, and this is conductivity. And you can simplify this equation to be the second equation here, which is just a function of the permittivity, complex permittivity for non-ferromagnetic material. So here, because they are C naught, mu naught, and the Zm can be measured from the reflection coefficient, you can calculate the kappa prime and the kappa double prime. So again, this is a kappa prime and the kappa double prime, right? And in here, unknown is only the real and the imaginary component of the complex permittivity. So if you measure this complex impedance of the material, then you can calculate the kappa prime and kappa double prime. Right? But for the non-ferromagnetic material, here you have this kappa prime and kappa double prime, and also their magnetic permeability are they are unknown too. Right? Those are mu prime and then mu double prime and kappa prime and the kappa double prime. Right? So because you have 4 unknowns here, you need to have more information about from the measurement. So in this case, you need to measure the reflective waves and also the transmitted waves to extract these 4 unknowns. But if you only deals with this non-ferromagnetic material, then you can just measure the complex reflection coefficient R star. Okay. So then how can we calibrate? So it's the same that we did for the low frequency measurement. Do you remember how we did it? So we did the short circuit measurement and the open circuit measurement. From there we extract the value for L of the inductance of the cable and the resistance of the cable, right? So it's the same. So if you just measure in the free space, maybe in vacuum or in air, then it's just an open circuit. So the reflection coefficient will be 0, right? No, sorry, 1. And this is I think conductive material like metal. Then this will be short circuit. So the reflection coefficient will be 0. And also you can put this probe into some known material, then you can calibrate it. And this is the way you calibrate. So you have a wave guide. This is the wave guide. And this is a coaxial cable, so the wave transmits through this cable and emits to the specimen. Okay. And this could be a sample holder for liquid, and I think this is for the solid material. So you do the open measurement in the open condition for open circuit, and you do the measurement in the short condition, so that you make a contact with the conductive metal specimen to the coaxial cable, the probe, and also you can test with the known material, with the known response of the material, like the DI water. Right? And as I said, the skin density is so small, so it will be only the local measurement, so it doesn't represent the bulk property. And the particle size, so for example, if the probe is like this, and this is the width, and the soil particle diameter should be smaller than the fifth of this width. So because if the particle is too big, then there will be a scattering dominant for the measurement, in the measurement. The another possible error that can be caused from the probe is the cable stability. So the electromagnetic wave measurement is very sensitive to the outside noise and how you insert the probe to the soil. So you have to allow time for cable to stabilize, and you should make sure that there is no air gap, because the air will act as a capacitor. And the sample thickness should be large enough to cover the whole penetration depth. Okay, so that was for the high frequency measurement. And so I think we should go. Okay, let's look at this chart. I think you remember that this chart, we learned this one from, I think, chapter 11, and it tells you about how the material can be polarized depending on the frequency. So if the frequency is so high, then you have an electronic polarization. That means that electron cloud can be polarized. And as the frequency decreases to 10 to the 12, then there's an ionic polarization. And as you go lower, further, then you have a orientational polarization, so that the water molecule can rotate according to the external electric field. Right? And here, so as you go, this frequency decreases, so the mass of the moving mass increases, right? So as you go further down to several megahertz, then there will be a special polarization. So it's like you have a clay particle, and the double layer can be polarized according to with respect to the external electric field. And we talked about this is the resonance, right? These two, and this is the relaxation phenomena, right? And we can simulate this relaxation or resonance phenomena with the LCR circuit. So, for example, when you have a mass on a spring and damper, and this shows the resonance or the relaxation phenomena, right, depending on the damper, right? So you can have a U versus omega and or the resonance or the relaxation. And just like that, if we have some circuit element like this, then this may give you also the relaxation or resonant type of behavior. So here, and when you get the impedance plot, you can plot it with the several parameters. For example, the common one is the spectrum, right? So the y-axis will be like impedance or admittance or permittivity, and the x-axis will be angular frequency or just frequency, right, in the logarithmic scale. And you can plot it with the kappa versus kappa double prime, and argon chart is the y prime versus y double prime, right? So these have all different names, and frequently we use the Coco chart and the spectrum and the argon chart. So let's do the analogy between the damped harmonic motion and the RLC circuit. Say that, so from the structural dynamics, we learned that if there's a force applied to this mass, so here the applied force is the F times sinusoidal function of the omega t. Right? This is the driving force. Then this driving force can be expressed with the acceleration term and the viscosity damping term and the stiffness term. And just like that, we can also plot this RLC circuit with respect to the charge. So you have an inductance term, and you have a resistance and a capacitance term. And here the driving force will be the electric field or the voltage. So the V naught times maybe sine omega t, right? And if we compare these two, the mechanical wave, or you can think of this as the mechanical, right? The elastic, and this is the electromagnetic. Then the variable here is the displacement u, and this is the charge in the EM electromagnetic wave is the q charge, and the coefficient of the variable here is the, in first order is the k, right? Stiffness term, and this is 1 over c. And here the damping coefficient, and R the resistance. And for the second order of derivative, here you have mass, and here they are inductance L. So elastic wave propagation or electromagnetic wave propagation, whether it's a low frequency or the high frequency, there's very profound similarity between these two. So driving term here is the force, oscillating force, and this is oscillating voltage, or the potential difference. And natural frequency is square root of k over m, and natural frequency is a square root of 1 over LC. So, like the Kelvin-Voigt model that we had, K and damper like this, and there could be another stiffness, right? So you can have tons of model which is composed of like several springs and dashpots, right? And here also you can make a model composed of several inductor L and the resistor and the capacitor. And we're going to review the basics of this LRC circuit model today to represent or to model the relaxation and resonance behavior. Okay? The first one is the resonance behavior. So if you put the R and L and the C in series, then this will give you the resonance behavior. Okay? So first, if you calculate the admittance, let's say that this is impedance, then what? Impedance will be just the R plus what? J J omega L and minus J omega C 1 over C, right? Because they are connected in series. So if you calculate the admittance, complex admittance Y star, then this will be just the reciprocal of the 1 over Z star. So it's like this. And from this, if you calculate the imaginary component and the real component, you can plot these graphs with some the parameters like this. Right? The R is here, the 500 kilo ohm, L is the 4.52 times 10 to the 3 Henry, and the C is the capacitance, right? Picofarad. So then if you plug these numbers to here, then you can plot the Y double prime and the Y prime versus the omega, the frequency. And also you can extract the real and the imaginary permittivity. So you can see that this is the resonance behavior with the peak, with the loss term having the peak at the resonant frequency. So using this circuit, then you can, let's go back. Yeah, you can simulate this kind of a resonance behavior. And that's going to be ionic and electronic polarization. Right? And for the relaxation behavior, there are several circuit models in the textbook. We're going to review two of them. And one is the divide relaxation model. So here you have a capacitor and a resistor in series, and there's another capacitor in parallel. And admittance, so let's say that this first one, what will be the Z of that? R plus minus J 1 over omega C1, right? And C2 is just the C2, right? So that's gonna be minus J omega C2, 1 over omega C2. And because these two are in parallel, so Y star will be Y1 star plus Y2 star, that's 1 over Z1 star plus 1 over Z2 star, so that you can have, you'll end up with this equation. And in this model, the resonant or relaxation frequency, so the relaxation frequency will be 1 over R times C1. And divide relaxation can represent the polarization of the water molecule. So orientation of polarization of molecule can be modeled using this divide relaxation model. And if you plot it, you can see that you have Y double prime and Y prime, and here the relaxation from the upper limit of the kappa prime to the lower limit of the kappa prime. And the second one is the Maxwell's interfacial relaxation mechanism. And here you have two elements. So this Maxwell relaxation mechanism captures the interfacial relaxation. So here that you have one element with certain permittivity value, and this another element with the other different permittivity value. Then if there's a one external electric field applied, then because these two have different polarizability, so there will be some charge accumulated at the interface. So this is the element 1 and this is the element 2. And if you calculate the complex admittance of whole system, then you have this final equation. And of course you can calculate it, right? Because we know that what's the impedance of each R and the C. And this can be used to simulate the interfacial behavior between the solid and the water. So let's say that you have a clay particle in contact with the water, then water is one lossy capacitor here, right? And the clay will be another lossy capacitor here. So these two are in contact with, and this will reflect, this will result in the polarization of the double layer, and this model can predict that behavior. So you have a polarization, the relaxation like this, and decrease in energy loss or the permittivity, imaginary permittivity with the frequency like this, which is ohmic loss. And the relaxation frequency is calculated like this, and these are all just plain definitions of each parameters. And the last one, okay. So here you have two material mixed, and each material is modeled as a lossy capacitor, and it can be applied to the two-layered material and captures the special polarization. So then, why we use this kind of a circuit analogy? So imagine that you have a rock fully saturated with water or some oil or mixture of the oil and water. Then you want to find the permittivity value or the electromagnetic property value of this effective media, right? Then you model this media depending on the frequency. If you expect this will give you the relaxation behavior, then you're gonna use this Maxwell circuit, and you assume this model and apply it and extract the R and C value from the measurement. Then you can convert it to the kappa prime and the kappa double prime. So this is kind of a fundamental model to extract the material property as a function of frequency. Just like that you use the spring and dashpan model for the viscoelastic material. So far, any question? 질문이? Okay. Then, as an example of using this L and R and C element, say that we have a clay particle which is solid, and there's a double layer in this clay particle. So you have a water, and if there's a current flowing to this direction, or the electric field is applied to this direction, then this clay particle will act as a lossy capacitor like this. And here this part, electric field will apply to the water part, right? And here, another water and capacitor, right? And there's another water layer at the top and bottom. So you can simulate this clay water mixture with these 5 elements. So this is the water layer, and water layer at the top and bottom, and this is the water at the edge of the clay particle, and this is the clay particle solid itself. So you have a Y1 star, Y1 star, and Y2 star, and Y3 star. So basically there's a 3 material are connected each other, and this can represent the one clay particle surrounded by the double layer of the water. Then the equivalent, the total admittance Y star will be this one. And if you can plug the R1W, C1W, and RWCW, and RP and CP, right? So P represents the particle to this equation. And then if you manipulate the equation, then you end up with this final equation, which is a function of water permittivity and clay permittivity, the solid itself, and the geometric parameters, alpha and beta. So here the alpha is defined as the aspect ratio, the length of the solid particle, here the length, divided by the thickness, and the beta is the water thickness divided by the solid thickness. And you can think of these particles are, there are a bunch of particles connected, so that this can be just one element to the overall whole system for the maybe centimeter scale of the specimen.